chance of an event taking place, before one can define a probability, you must know what the sample space is. A sample space is a collection of all the possible outcomes when an experiment is conducted. So for example, if you add a red color with green, you expect something to occur. That's why you experiment that. If nothing happens, that means probably you never even tried, because as soon as you combine some of these colors, they change to a different color. If you add a coffee to hot water, it melts. And the scent of the coffee can take over the room easily. So that is the experiment, and that's what happened. And most of these companies have been experimenting some of this a very long time. And that's why they've established different type of coffee shops around the country, and they have been able to convince you and I that, hey, if you need coffee, come to our shop. Some of you would like to go to this A, other one like to go to B. Why? Because they keep on experimenting, and they come up with new things like, hey, we got a new one. We can even put whatever in it. You go for it. So probability is full of experiment. Now, once you're able to put all the outcomes together, you can then think of an event. An event is a subset of the sample space. And then you can define the probability of an event, which is the number of elements in that event divided by the total number of elements in the sample space. I gave you the simple rules that probability must be between 0 and 1. It cannot be more than 1, neither can it be less than 1. So probability can never be negative. And then the probability of the sample space is 1. That is, we have 100% certainty that is going to occur. Like you coming to class today, you were 100% sure of coming. Are you going home today? Yes. So it's 100% chance that you're going to get there. But some few things can occur. Probably the train can break down. Anything. Like nobody knows. Life is full of uncertainty. That's why we have insurance. So insurance companies depend solely on probabilities. If you're a new driver, they calculate the probability of a first driver having an accident so that they can charge you big money. In this state, I think after the 6th year, that is when this thing, the premium goes down a little bit. Everything is probability. If you ever think of working for a probability, an insurance company, apart from those writers and the rest, everything is probability. So from there, we talk about when you roll a die. You roll a die, 1, 2, 3, 4, 5, 6. If it's 2 dice, you're going to have 36 of them. We play around with that. I gave you a lot of questions on that. We looked at the at least, which means that number or more, and the at most, which is that number or less. From there, we talk about the coin. We toss some coins, maybe a single coin, and we also look at 2 coins, and then the last part was tossing 3 coins at a time. We had 8 outcomes, and we had a whole lot of questions under that to play with. I think that's where we ended. Today, we want to talk about what we call compound event. Now, this compound event means that we are not just looking at one thing, but we're looking at 2 things at a go. Let me take you back to what you know and you can relate easily. Now, you remember when we started learning English, they started with statement, sentence. They call it simple sentence. So it could be that Albert is going to school. And then we have another one, which will say probably Ernestina is also going to school. We have 2 of them. But at some point in time, they said, oh, can't we put the 2 together? Then we say, yeah, we could. So how do we put them together? They started giving us what we call conjunctions. And, or, either or. And so you could say, Albert is going to school, and Ernestina is also going to school. It becomes a compound statement. Does that make sense? That's all we're trying to do here. We will be using these conjunctions, and, or, to bring 2 statements together, or 2 events together. I believe you have the picture now, right? Now, once you have the picture, we can talk about the statistical aspect of that. we will start with the or. So assuming we have a probability A, an event A, and another event which is called B. Can we put these two together? Yes, we can say A or B. So that becomes probability of A or B. In statistics, especially under probability, whenever you see this word or, it means addition. So here we have the addition rule. And the addition rule states that A or B is equal to that. This is a formula which we will be using in solving any problem or any probability question that involves or. So anytime you hear of or, know that they are talking about the addition rule. Or means addition. Keep that in mind. I'm going to try to break this formula down so that it will be much more easy for you. There's no need to memorize it because it's on the formula sheet, or I can even provide it when you have a test. But learn how to use it. That is the most important. Of course, that's why you're here. So we are saying A or B is the same as probability of A, which is the first one, plus the probability of B minus probability of A and B. Now this is not or. This is the statement. Now this A and B, no, not yet, is what A and B have in common. Intersection. So this end, as we saw on the other side, can be interpreted as what two events, or probably two or more events, have in common, or multiplication. We are not at that multiplication stage yet. So whenever we see end from now on, you want to think of it as what they have in common. Let me make things easy for you. I always tell you probability is not in the classroom. So now let's go outside. You know there's a road somewhere there, just behind this building. It's called New Rutherford Avenue. You know there's another one there. What is the name of that one? Which goes to the Charlestown? Oh, you don't know the name? That's okay. But let me give you the picture. This is Bunker Hill. Behind Bunker Hill, this road is over there. And then if you want to move from here to the other side to buy food, you go over that bridge. Now, this road intersects with another one there, right? This intersection is what we call the end. What this road and that road have in common. Is that okay? Yeah. They meet. They have something in common. That's what we're referring to as end. And I probably in your neighborhood, you see all these things. Wherever you see a traffic light, the two road or the two streets have an intersection. So you get it now, right? Where the traffic light is situated, intersections, and what the two roads have in common. Is that okay? Mm-hmm. Good. So let me use some.
Wait, is it that they can go like in any direction, like in terms of like math, or?
I'm trying to understand.
That you can add or multiply or subtract or whatever. Or
add and multiply.
Yeah. When you talk about in like intersection.
This is what they have in common. So we're going to find out what they have in common and put it there. But when it's time for the multiplication, we will give you another condition. But for now, we don't really want to think about it because I haven't even mentioned it. Let me give you a mathematical example. Now we move from the outside to the classroom. Now suppose I have a set called A, which is full of some alphabetical letters. B. So we have the alphabet here. D, F, G, M, and K. This is set A, right? That is set B. You know we can find A and B. What these two have in common? What do they have in common? D and F. That's what we mean by what they have in common.
So if that's a value, it's gonna go inside.
We're going to use that to explain that in a second. We're going to use that to explain that in a second. Is that okay? Now, if I write A or, bless you, B. Now look at it carefully. A or B means addition. Addition means combine. So A or B means put everything in A and B together. Does that make sense? So I'm going to write everything. A, B, C. There's no C. E, D, F, and H. And in this one, I have D, F, G, M, K. Right?
So you do
But-
write them twice.
Good. Now you notice there's a double counting over here. We have counted D here and also D here. We counted the F there and the F there. We've counted some elements twice. In statistics, it is very important to avoid that. So how do we take it out? That is when we take out D and F. Follow carefully. We counted some elements here twice. Which element did we count twice? D and F. So I'm taking one of them out. I took one D out and I took one of this out. Now this part, which was just taken out, remember it's A and B. That is why in this formula we have minus A and B. It takes care of double counting. It's not just a formula. Make sense? Because you're going to combine A to B, counting everything. What if they have something in common? You are counting both of them. Take it out. So now that we kind of understand. Yes.
When we're doing the equation, you're going to want to start with the A and B.
Don't do anything yet. I'm going to show you how to go about it. Yeah, otherwise when you go ahead, it's going to be messy. So for now, let's stay with me. So far, so good? Everybody comfortable? Awesome. Yeah, let's try. So let's see if we can do some examples on these, right? And I'm going to introduce contingency tables. Yeah, let's think about DMV a little, or DM. We call it DMR, DMV, whatever you call it here. Here is. You go to some state, it's DMV. You come here, it's RMV, it's DMR, whatever they call it. So RMV. Now over there, we have drivers, right? And drivers, we have two categories: those who have had accident before, and those without accident. You got it? Also among drivers, we have female and male. So I'm going to combine the two and put them on the table. So follow. Maybe it makes sense. So we have the female drivers. I'm just creating a table, constructing a contingency table. And the male driver. Now those who have had accident before and probably no accident. So suppose I put 3, 10, 17, and 15. We should be able to understand everything on that table. So I've given you a table. We're going to try to understand it. Once that is done, we will turn it into our, what do you call that one? My math lab thing. And then get some questions from our textbooks. Because I believe your homework may be similar to today's. My math lab, whatever. My math lab, okay. The C. And there's an X. Great. We'll get there. So, what is the meaning of 10?
10 males had no accident or had accidents.
Did you understand that? She said 10 males who have had accident, right? So we have 10 male who have had accident. So we're talking about two things, but then we're using just one thing to represent them. Mathematically or statistically, this is what we're trying to say. Accident and male. And is what they have in common. They are males, they are drivers, but this is how many have had an accident. How about 17? Female, no accident. Make sense? Great. Now, suppose we have this type of table. The first thing you want to do is to find the column total and then the row total. Because I can look at this table and ask you, how many drivers have had accident before? How many? 13. That is the total. So we have 13 who have had accident before. How many drivers have no accident? 32. So you know how many drivers are we talking about? 45. I hope you all follow. Now, how many females do we have in our data?
20.
And how many males? 25. So you see, we just found the total of each of these. And this is a contingency table. And I think you're going to have one of these on the next test.
What number is it?
I don't know. You know, I decided to switch question 3 and number 6 on this test, and most of you were confused. Remember question 3 on the chapter 10, it was r squared. I decided to move it to 6. Like, come on. Okay, I'm never going to tell you the number. I will tell you to be on the test so that you don't go say, oh, this is number 1. No. That alone could mess you up. I'm like, no, this is not supposed to mess you up. I want you to get 100.
I think it's because we went through the 6 steps so many times.
And
that's what we planned, and we planned for
for
and you threw that all out the window.
Yes, I know. So I guess that was my fault. That's why I'm moving away from that. Sorry, I'm moving away from that. It's never going to happen. All right. So we have a beautiful table. What is the sample space? 45. That's the number of elements you have in the sample space. So if I ask you to find the probability of female, can we use F for female? You okay with that, right? What would be the probability for female? That's what. Find the probability of females. How do we know it's 20 out of 45? Because we have 20 female on the table. And the definition of probability says that it must be the number of elements in the event, which is the female, over the total. 45. Do we have to simplify this? I don't care. By probably my math lab, they'll tell you what they want. I'm just interested in your understanding of the subject material. What's the probability of accident? Probably A. 13 out of 45. Are we, is everybody okay? Are we on the same? Awesome. What is the probability of male and accident? 10 out of 45, right? Male and accident does not mean this and that. It means one thing. What do they have in common? Remember, I just used street to illustrate that. You can do the same thing even on the board. Watch. Male, right? Accident. That is the point of intersection. You draw a line through them. Even if you have no idea, you can use this same idea to get the answers. How about probability of female and no accident? How much? 17 out of 45. Any concerns? So far, so good? How about probability of male or accident? We do which one? What? Say, waiting. Which one? Is it the same? No. So what do we do?
Add both.
It's all of them, add them all together, like, all the potential for accidents and all the males. No?
So 10 out of 25.
Plus,
Addition.
Or is it addition?
So
10 out of 45.
Oh.
10 plus 13. 10 plus.
Wouldn't it be like the two, like all the males minus, like the no accidents minus, the potential for no accidents?
No, it's male minus female accident. You take out the female.
Yeah,
accident.
minus the double, the one that counts twice.
this is the formula.
So 10?
Anytime you see or, use this formula. So you use the addition rule. Unlike the individual event and then the one where we use the and, what they have in common. When it comes to or, this is your formula. I hope this is even going to awesome. That is your formula. And you can mimic it. I mean, you can always rewrite this in your own way. This is it. Probability of A, I think I even wrote that on the board. Probability of the first one plus the probability of the second one minus what the probability of the first have in common, right? So I can rewrite this formula or this question as probability of male plus probability of accident minus probability of male and accident. Any concerns? If you have any difficulty, let me help you address that. Great. So now we go. What is the probability of male?
25.
What's the probability of male? 45. Thank you. Plus, what's the probability of accident? 13 over 45. And what is the probability of what they have in common?
10.
Does that make sense? Do you get this part? You get this part? This is the part which is an issue, right? What is the meaning of male and accident? What they have in common? So you go to your table, male, accident, intersection, 10. It's simply because you counted this 10 twice. When you were finding the 13, you used the 10. When you were finding the male total, you use the 10 again. Great. So you need to take the 10 out. And from here, this takes us to 094 or 097, whatever it is. You must be able to do that. This is not statistics. Anyway, they have the same denominator, so you can combine the top. So what is that? 28 over 45. You can simplify that if you want. It does not affect your answer in any way. Whether you give us a fraction, a percent, or decimal. It's the same thing. All right, another example. What's the probability of female or no accident? What do we do?
Take all females.
Not yet. Let's write the formula first and then. So, P of female, excellent. Learn how to do this because you may be required to do that. Plus, P of no accident or accident free. Minus P of female and no accident. So from there, you can then substitute the numbers. Don't do it in your mind. You end up making mistakes. So what's the probability of female? 20 over 45. You go to your table and pick the numbers. What's the probability of no accident? 32 over 45 minus, what's the probability of what they have in common? 17 over 45. And from here, you know I don't have to do any other. Maybe you may have 35. Right? If it's wrong, change that. Out of that. And this is how these insurance companies do the computation. They find the probability of those who had accidents in the first 6 years. And it will surprise you to know that it's almost up there. Big number. That's why they charge a lot, because if they don't, a lot of accidents will occur, they will not make profit. But after CC, everybody is careful. You've been paying insurance for a very long time, so when it goes down, psychologically, you don't want it to go up again. So you try your best to be careful on the highway, on the bypass, wherever you are. And so it stays down for a very long time, and they make more money because we are accident free. They hate snow. They hate black ice. They hate a whole lot of stuff that man cannot control, because the more these things occur, the more money they pay out, and they don't want to be dishing out their money. They want to make more money. If you want more money, learn successes, go to insurance company, make a lot of money. They make a lot of money. Great. So far, so good. You get this picture, right? Wonderful. Let me introduce another side of the compound event. I think your compound event should be okay for today. We're going to do a lot of examples afterwards. This is a definition. Mutually exclusive event. Two events are said to be mutually exclusive if they have nothing in common. They have nothing in common. Mutually exclusive events, it means they are disjoint. A quick example would be Highway 93. You know, we have the south and the north, they never meet. Two separate roads, they don't meet anywhere. Mutually exclusive event, that's the highway. And most of these highway, IA-80, Highway 80, 91, 95, 26, 95, whatever you call it out there, they don't meet, especially when you have the north and the south. Can run from one end of the country down to another side. They don't meet, maybe side by side. Mutually exclusive event. So they have nothing in common, right? Now we can bring that to the board. Two events have nothing in common. And if they have nothing in common, that means that their intersection is going to be zero, right? Because there's nothing there. And that is what we have. That is why we have this here. So it is supposed to be that is, not that. Put the is in there. That is PA and PB is equal to 0 because they have nothing in common. Can we do an example on the board? Of course. What is the probability of female and male? What's the probability of female and male? What do they have in common on the table? Nothing. How do we know? If we draw lines through them, they don't meet. Parallel lines. So this is 0. Oh, he is a male. He's also a female. These days, everything is possible. So I don't even want to go there. But let me go here. I think over there, I can say more about that. Accident and no accident. Is it possible that you've never had accident before and you've had accident before? Tautology doesn't even make sense. So if I ask you to find probability of accident and no accident, you know that is 0. Why? Because it's mutually exclusive event. That's the first definition. Good? Now let's talk about independent event. This is when the multiplication comes in. Now you notice that each of these definitions involves and. This end here, what they have in common? They have nothing in common. But then now, this end is now being translated as multiplication. So why the change? It's simply because of this word, independent event. Anytime you are told, or probably you figure it out yourself, that two or more events are independent. In this class, you will always be told, so you don't really have to worry about it. If I give you two events that are independent, I will tell you these two events are independent. And for that matter, you should be able to change the end to multiplication. If they are not independent, then of course we are still using the up one, the one above it, the mutually exclusive event. Now let's explain the independent. Two events are said to be independent if the occurrence of one, or probably the non-occurrence of the other, has no influence on the other. Let me give you some examples. Most of you have traveled by air before, right? Or by bus, or by train. Oh, train a lot. When you wake up in the morning, decide to come to school, do you think of other passengers who will be taking the train that morning? No. All you know is, I've purchased my ticket, you get on board, they will take you to Bunker Hill. I've purchased my ticket, I'm going to the Bahamas, I don't care who else is going to sit on the plane. What I know is on that day, the airplane company will take me there. So when you are purchasing your ticket, and another person is also purchasing the ticket for the same plane, your decision independent. You don't care who's going to be on the board. Usually I don't want people to be on board so I can stretch, sleep, and then wake up. It becomes a first class in the wherever you were sitting. But it's full. It's another thing altogether. That is independent decision. This morning or this afternoon, before you even entered this class, did you even care about those who are going to be here? No. Your only concern was the professor. Is he going to be here? If I'm not here, you'll not show up. Of course, why are you going to be here? But you don't care about the persons to their left and right. We've all paid for it. And that's true. No, it's statistical. It's mean, but it's statistical. But you know it's true. That is independent event. Unless, of course, we are friends or buddies. You give me a call. Hey, you're going to show up in this statistics class. No, I hate that guy. No, let's go have fun. Now your decision has been influenced. In that case, it ceases to be independent. I hope you understand independence now, right? Yeah. Good. But statistically, whenever you see independent, it means multiply. Change this to multiplication, period. Is that okay? So I'm going to give you an example on the mutually exclusive, probably, I don't know, independent, so that you have better understanding of that. I'm going to write on the board. Probability. Independent, dependent, independent. Probability ideas. Okay. On a given day. Oh, okay. On a day. Let's make it in a day. In December. The probability that it will snow in Boston is 0.4. And the probability that it will snow in Moscow is 0.7. Assuming independence, find the probability that it will snow A, in both cities. B, in neither city. C, only in Moscow. D, in exactly one city. Yeah, I think the rest of the lecture will be dedicated to examples. After this, I'll try to do another example from your textbook if we have time. Great. So this is what we have. On a given day in December, the chance of snow in Boston, 0.4, it's about 40%. And the chance of snow in Moscow, 70%. Assuming independence, find the probability to snow in. So, what is the meaning of this? In both cities? Ah. In what? And Boston, right? So you were not told it's and, but that's what this means. Both cities, this and that. Make sense? So how do we solve this problem? Why are we supposed to multiply them? Excellent. You were told that these two events are independent. And so if they are independent, then by definition, you must change and to multiplication. So this becomes probability of Moscow times probability of Boston. So far, so good? And what is the probability that it will snow in Moscow? 0.7 times, or let's do that. What's the probability that it will snow in 0.4? And you multiply the two. So there's a 28 chance that it will snow in both cities. Can we go to the next one? Neither city. What's the probability to snow in neither city? Why 0? What is the meaning of neither city? What is none? What is not possible? Chance of snow. Not possible where? In both cities. That's what this statement means. What it means is it will not snow in Moscow and not snow in Boston. Right? That's what this statement means.
Does it imply that they're mutually exclusive?
No, we don't know. Nothing has been said, so we can't tell.
Wait, what?
It will snow in neither city. And somebody said that means it won't snow in Moscow and it will not snow in Boston.
So would it be the multiplication of the difference, like 0.3 and 0.6?
How did you know it's 0.3?
Because you have to get to a hole.
You have to get to a hole. Do you remember that? We talked about that, right? Complement. The probability that it will not occur. We even use alpha to talk about that in chapter 10. It has come up again. So what is the probability that it will not snow in Moscow? 0.3.
I'm sorry, where did you get that?
Yeah, ask where did you get that? The complement of an event.
So it's 0.7.
0.7, you take it away from 1. So this is like 70%. This is the chance that it will not occur is 30.3. And not in Boston. That would be 60 because we know that we have 40% chance of snowing.
Isn't that the correlation coefficient, the probability
The
that it
alpha-
doesn't happen?
That's the yeah. So this time instead of thinking of it as that, we call it the complement. It's all over.
It matters.
0.6. Multiply the 2. 0.18. Are we okay? I'm only introducing the concept of independence. That whenever we see end, we change that to multiplication. If it's mutually exclusive, of course, there's nothing in there. But here, nothing suggests that. I think I'll be doing C on the other side. Part C. What is the meaning of that?
Probability that it will snow in Moscow, but not in Moscow.
Excellent. Because we're talking about 2 cities over there, and it's going to snow on that day in Moscow. That means it is not snowing in Boston. So probability that it will snow in Moscow and not in Boston. Right? So this then becomes probability of Moscow times probability of not Boston. And what's the probability that it will snow in Boston?
No, 0.7.
Excellent. Times the probability that it will not snow in Boston. 0.6. And that for 2.
Is it easier to change a problem into percentages?
If you like, excellent. I think that's a good suggestion. I mean, for those who hate decimals, it's a good idea because percentages, decimals, and fractions are the same. That's why personally I don't care about how you express them. Once you understand the concept, yay. The numbers you deal with it, you were taught that in probably 097, 093, whatever. But I think what he says is a good idea, like, hey, you don't like decimals, change it to percentages and work with percentages. It makes things easy. Or if you like fractions too, change to fractions. Like, so far so good? I'll do the last one. Or probably we will, as if I'm doing it, you are doing it. What's the meaning of it will snow in exactly one city?
Well, they don't mention which one.
So, that's a good start.
You just choose one.
I like the idea, but don't just choose one, but state both.
Oh.
So it's possible for it to snow in Boston, right? And you know if it snows in Boston, because it's exactly one city, then it will not snow in Moscow or this time it will, Moscow, excellent. That was a good start. Not in Boston.
But that's saying that they're mutually independent then? I don't understand why. If there's a probability that it will snow in Boston, how does that negate the fact that it's not going to snow in Moscow? It could snow in both places.
That was the first part, when it snows in both places. But the last part is it's snowing in just one city.
So does that mean if it's snowing in one city,
It's not snowing in the other. That's what they're saying. So we just weighing that. Probability that a young guy will have an accident, but an adult will not have it. or the other way around. So insurance companies can charge you money. Probability that a student from Dorchester will graduate, but not a student from Revere, or probably the reverse. And the school does all this side of computations. That's when we get some beautiful data and tell you, oh, of all those who come through Bunker Hill, this percentage are from Africa, this are from, percentage is the same as probability. So you can find out who are graduating, who are dropping out, and then probably we put some remedies in place to help students overcome that. And I believe most of you know that we have an office across this place, right? We have a beautiful office up there called Single Stop. Whatever you need, insurance, money, whatever, food, as long as they have it, they can help you so that your academic life will not be jeopardized or whatever it is. Yeah. And they even have free tax going on over there. So if you haven't done it yet, just walk in is free. Pay nothing, they do it for you. Good. Anyway, let's continue with this one. So the first part, if it snows in Boston, the probability is 0.4, right? And is when it does not snow, so it's 0.3, yeah? What's the meaning of or? Addition. Probably that it will snow in Moscow, 0.3, and not snow in Boston, 0.6. So do the computation. Yes, you do one part and the other part, and because it's or, you add them and get the answer. And as I said, this is just the concept of independence. I'm just trying to introduce independence to you. Now I will take my last example from your textbook, the electronic. And this is our sisters here. Chapter 4. Which part of chapter 4? I think we are at 4.3 or 4.4, I don't know. Somewhere there. Multimedia. There's a beautiful question there on the table. You see, this is one of such problems. And we use this even for cancer analysis. You know, sometimes you go through did they call it the mammograph? Mammogram. Yeah. My mind is full of graph. Mammogram. And to determine whether or not you have it or not. Sometimes they tell you it's positive, but when a further, analysis is done, they tell you, oh, we're sorry, you did not have it. Or sometimes they tell you no, and then later find out it's positive. They call you back. We have all these things going on. So now look at this. We have this dosage, correct dosage calculation, wrong dosage calculation. It happens in the hospitals too. Some nurses are killing us, including the doctors. So here we have the ratio label, concentrated label, so many things. This is a beautiful table, which is similar to this. And if you are asked to do anything, you should be able to do that. That's not what we're doing anyway. I'm trying to... this is what I want us to consider. Blow it out a little bit. I hope that is the one. Yes, it is the one. Get out of the way. Beautiful. So let me read from the top so that you get a picture of what is happening. We're supposed to use this table to answer so many questions, but I'm going to do few. 27 through 32. Refer to the following summary result from a study of people who refused to answer survey questions that were sent to them. I hear you knocking, but you can't come in. Yeah, I tell you all the time, it's very difficult to gather information, right? If you come into my house to get information, you don't have money to compensate me for my time, don't show up. I won't mind you. So I have better things. That's the way it is. Or they send it to you, and who is going to post it back? No, I'm not doing that. So by Fragrance and Fuller and Sociology, blah, 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 blah. In each case, assume that one of the subject is randomly selected, right? So now let's familiarize ourselves with this data, and then from there we can continue. That's the good thing about data. If you look at the table and you do not understand it, don't do any work on it. Because you mess up. Number one, you don't even know what you're doing. So let's try to understand what is going on, right? What is the meaning of 225?
Just the amount of people who responded.
22 to 29.
Ah, the amount of people who responded whose age between 22 and 29. What about 16?
40 through 49.
Excellent. So these guys, ages between 40 to 49, they got whether the email, the thing was sent through the mail, but hey, forget about it. I'm not responding. 49, the same thing. 60 and over, 49 of them decided not to respond. 202. And a lot of these government agencies do some of these classification when it comes to administering some of these administrative instructions or instruments or whatever they call it.
How do they know the age if they refuse to take the survey?
It's because, for example, if I send something out to this class now, I can break it to 19 to 21, 22 to 24, 26 to that. So it's part of my questionnaire. So when I give it to you, you have to check off and belong to this age. You know, some of these things even happen online when you are filling some of these forms. So it's already categorized or probably stated on your questionnaire. So before you even answer their question, you tell them what your age is, your color, and other things. When you are filling these application letters, it's pretty common, yeah? It's all around. Even in this school, they tell you where this part is not really important or it's not obligatory. Tell us whether you're black or white. Tell us whether you are Hispanic. And then they talk about so many things. Are you the first person in your family to go to college? They tell you, they ask all these things. So the age is asked, and then they classify everything. That's when they get to know, oh, of those who responded, 16 of them between these ages, because they know the age. You've already stated your age, so they can tell. Good? Great. So we have an understanding of this, right? Before we continue, what are we supposed to find out first? Awesome. Because without the total, you can never find probability. Is that okay? So, I have 3. Let's start with the first one. This is coming from page 176. If you're interested, put it down. And the question, I think, is 37 to 32, 27 to 32, so one of them. Page 176. This is the e-book, not the physical book, because the page numbers differ. What is the probability that a selected person refused to answer? What is the probability that the selected person refused to answer? That's right. So for those who refuse to answer, this is the total, right? So we need to find a subtotal, as we did on that table. Remember that? Good. So put it together. I'll take it. 156. What about the top one? Yeah, we have time. A lot of time. And what will be the total? So you noted that we were not told of the number of people that were surveyed. Yeah, that would be 1205. This is the total, yeah? And we can also find the column total. Let's do that quickly. 84, 275, 78, 152. Is everybody okay with that? Great. With that, I think we can now. So what is the probability that a person selected at random does not respond? So 156 over 1205. This is the answer to question number 27. That's it.
Is it P equals?
P.
Yeah, you write probability.
Oh, yeah, you can write probability of refused. Oh, is that refused? Yeah. That's it. It's equal to that. 28. A pharmaceutical company, they should be interested in these people because these are the people who consume. medication. And we get in there gradually. We get in there. We may need it for our bones, for our knuckles, from all sort of. So a pharmaceutical company is interested in the opinions of the elderly because they are either receiving Medicare or receive it soon. What is the probability that a selected subject is someone who is 60 and over, who responded? Now you got it. 202 over 1205. Done. 29. Survey refusal. What is the probability that a selected person responded so the selected person responded or is in the age 18 to 21 bracket? So what do we do?
So, because they're independent, you multiply them, right?
Yes, you multiply them if it's independent.
So 1040 or 1049 times.
And what makes we feel that it's independent?
Independent is the 18 to 21-year-old bracket.
How do you know it's independent?
Because they decided they wanted to
They want
respond or
some-
not.
No, you are never.
Elected persons who responded. So you have to, you know what that is. It's all those other categories exclusive of 18.
The other one.
They want you to separate that.
You were never told it's independent. And so you don't assume independent. In this class, if it's independent, I will state it, just as I did in that statement.
So do you want the probability of all the people?
No, what is the meaning of probability responded or is in that?
Like the total of people that responded and the total of people that.
The addition of those elements? So 1049
Everything
plus
plus that
73?
set, plus that group?
Use the formula or addition rule. Don't forget that. It's going to be on the test. Or addition group. Make sense? It's or. Anytime you see or, stop thinking about it. I know how to figure it out. Use the addition rule. My last example. So, this is how you set it up. Probability of those, we're talking about those who responded, right? Or they are between 18 to 21. That's what they asked, right? So this will be equal to, help me write it out. P responded, call it R, plus age between 18 and 21 minus P responded R and 1821 have in common. Is that okay? Now, what's the probability of those who responded? 1049 over plus what is the probability of those between 18 and 21? 84 over. Now, what do they have in common? How do we even know? Draw lines, as we've been saying. This guy and that guy, that is the point of intersection right there. That's the end. What they have in common. 73 over 1205, and I believe the rest is calculator work. Beautiful. When you go home, continue with the rest. We'll do more examples on Thursday and move on to another step.